All right. This is a reproduction of the Artificial Intelligence and Games, a two-way street presentation that was given at MagFest 2022 in January, with a little less theatrics, but otherwise content is the same. So here's the whiffum, the what's in it for me. If you want people to pay attention to you, you have to tell them right up front why it's in their interest to you. Some people used to call it the what's in it for you, but that was pronounced waifu, and you weebs have destroyed that, so now we call it the whiffum. Every gamer has dealt with AI. Every game designer has designed AI. AI research has contributed to lots of games, but now games contribute to research, and it's at the point now where it's a closed loop. The last 5 to 10 years of AI research have been quite explosive. AI has changed from hard coded to machine learned. We'll discuss some research challenges and milestones, and we'll talk about what the AI revolution means to you as a gamer, as a dev, and as an artist. So, what's the agenda? We'll talk about an introduction. I'll tell you who I am and why you should care what I say. We'll try and fail to define AI and talk about what it is and give some examples in games. We'll give you some examples and challenges of applications, of research, make some predictions for how the future of AI will look, and then I'll provide some advice for gamers, devs, and artists about how to use AI tools and weather the changes that AI will bring to us. So, who am I and why should you listen to me? My name is Chris Daly. I have an undergraduate bachelor's degree from the U.S. Naval Academy in computer science. I have a graduate degree from UC Berkeley in information and data science, and I currently work as the head of artificial intelligence at Electronic Warfare Associates, which, as the name implies, works in the wireless and radio frequency space. My current research is radars that learn to operate themselves and radios that learn to jam other radios on their own. Those are my technical creds, my gamer creds. I didn't think The Lion King for Sega Genesis was that hard. I know it was a long time ago, but it's kind of a meme, and anybody who played games back in the day knows why that's significant. I was a nationally competitive Soul Calibur 2 player, and my Steam library has had a scroll bar since 2005. So, what is artificial intelligence? Well, we don't actually know. Kind of like the word life, the word intelligence has avoided rigorous definition for as long as it has been researched. It's common for computer science professors to challenge first year CS students to define what a computer is. It turns out it's surprisingly difficult to arrive at a definition that includes everything you intuitively think of as a computer, but that also excludes humans. You might think a computer has to be silicon and electricity, but you can make a Turing complete computer with marbles, pebbles, slime mold, water, even live crabs. The same is true of intelligence. There's no accepted definition for it. Alan Turing famously posed what we now call the Turing test, where a human sits in front of a computer and chats with someone. If the human thinks the person on the other end is a human and it's actually a computer, the computer can be considered intelligent. The test isn't very helpful because it's subjective, inconsistent, and applies strictly to natural language processing. But beyond that, we don't have any way to define intelligence. It should be obvious then that we don't have any rigorous way to define artificial intelligence either. But for practical purposes today, we can loosely define AI as any system that makes decisions or take actions that would otherwise be made or taken by a human. Lots of stuff falls into this category. The original steam engineer included a weighted rotary component that we see here, called the centrifugal governor, that automatically increased or decreased the amount of steam the engine produced in order to keep it operating at a certain range. Normally, a human would have to make this judgment, but this was done mechanically by a machine. Boom, AI, no computers involved. Cruise control on your car, the thermostat in your home, the screen brightness adjuster on your phone, all of these accept some input and make some decision, potentially including taking an action. However capable the AI is, some initial decisions must be made. Some variables must be set by the designer rather than controlled by the AI, and these are called hyperparameters. For example, in the centrifugal governor here, it has weights. How much should each arm weigh? That determines how wide the desired speed range is. How much gas should the cruise control give the engine to speed up? Things like that. Artificial intelligence is mentioned nowadays in the same breath as machine learning, but they're actually not the same thing. In the examples we've discussed, all the rules and decisions patterns were designed by humans, so clearly AI can exist without machine learning. The tight coupling between the two has come about because of modern research that uses machine learning techniques to arrive at decision points and policies that are broader, more detailed, or better informed than a human designed system could ever be. These are the core of the topics of this talk, and we'll cover them in the critical role that games have played in this research later. So, what are some examples of AI in games? There's lots of examples. You probably know them if you're an experienced gamer and you talk about them without even realizing you're talking about them. But it's important to consider just how much is happening and how easy it is to ignore it and not give it the credit it's due for how difficult it is. In the upper right, you see a screenshot of Total War Rome 2. How does the computer decide where to move different units and armies? How does it decide what improvements to build in what provinces? In the top middle, you can see a clip from Soul Calibur, a Soul Calibur game. How does the AI know what moves to make at what time? How does it do it so that it's competitive and also so that it's fun? Um, we'll talk about that balance in a little bit later. In the upper left, you see another fighting game, Street Fighter II Turbo. This clip, by the way, is the famous Daigo Umehara outplay from EVO 2004. If you haven't looked up that clip, please look it up. It's probably one of the greatest displays of human gaming skill in history. In the lower left, you see a clip from League of Legends. There are levels of AI in League of Legends. There's the micro AI, where the AI has to determine when to cast what spell, when to attack you versus attack the creeps, when to push a tower, when to back off, when to recall. And there's the macro AI. How does it determine when to send the jungler to what lane, or when to rotate, one laner to another lane, or something like that? In some ways, it simply doesn't. Like, I don't think the AI knows how to jungle at all. But all of this stuff is still happening all the time under the hood. In the lower center, you see a replay of the game of the century played by Bobby Fischer in, I think, the 50s. And we'll talk about board games and how they've played a role in AI since the beginning of the field. How does it determine what moves to make at each time it tries to make a move? And in the lower right, you see the fight against Fire Ishin at the end of one of the endings of Sekiro. Uh, One of the things that shocked people about this game was how clean and smooth the AI was in fighting. And you can see in this case that Ishin makes this stylish and somehow fitting dodge that we as players did not expect when Sekiro came out. So, why is game AI hard? Well, first we have to define what hard means. Some games yield effective AI design very easily. First person shooter games, you can just set some waypoints around the map, random walk the agent, and give it a perfect aimbot. As soon as you show up in the view frustrum of the AI, it headshots you. How many times have you been escaping from Tarkov and some scav head eyes you from 300 yards away with an AK with no dust cover? Obvious bullshit. That's not fun and not realistic. Some players are very good, but no one is that good. Remember when Sea of Thieves first came out and the skeleton fort cannons were absolute snipers? Everybody hated it. Freemason Live is a streamer very skilled at Tarkov and Sea of Thieves and other first person shooters, and he'll often say that a fight was fun even when he loses. But no one says that about getting headshotted from across the map. So, how do you get an AI to play like a human? Well, in the most fundamental sense, an AI isn't really any different from a human. It boils down to an array of if then statements. In programming, an if then statement is just what it sounds like: if this condition, then take this action. An AI program to play blackjack can be easily coded this way. There are 250 possible openings in blackjack, so you could literally write an if then statement covering each of them. As the number of possible game states increases, it quickly becomes infeasible to write if then statements for each of them. In Slay the Spire, for example, there are 127 different relics that can exist in any combination, some of which have states of their own, like Pen Nib, which doubles the damage of every 10th attack. Assuming the player has just 3 relics, that's 127 times 126 times 125, which is more than 2 million possible game states. And that's just 3 relics. A typical run might accrue 10 or more relics. Then consider the different cards in hand, the possible HP the player could have at times, and the possible combinations of enemies, what turn it is, etc., etc. No way you are writing if-then statements for each of those. Jorbs is an exceptionally skilled Slay the Spire player with a very mathematically rigorous approach to playing the game, and even he often can't explain why the right play is the right play. Exhume seems better than feed here, he'll sometimes say. How do you program that? In 4X games like Civilization, each decision has extremely long term ramifications. You can take that in one of two ways, which we'll talk about here in a minute. So another way game AI is hard is long-range dependencies. A number of possible states to account for is a difficulty. Long-range dependencies are another issue. In Civ 6, the very first decision that you have to make is where to settle your first city. Settling one tile to the left in tile A puts you in range of horses. Settling on the tile to the right, tile B, puts you in position for a really good campus location. That one tile difference will dictate whether you develop a militaristic civilization or a science civilization. Hundreds of turns from now, when faced with the decision to make, the choice of tile A or tile B will make the play wildly different. In Rome Total War 2, how do you decide what to research? What to build in what cities? Some important things aren't even saved in the game state. When we talk about where to settle a city, that's only kind of a long term dependence because where you settle your city is saved in the game state. But there are long term dependencies that aren't saved in the game state. So, for example, if you settle next to Cyrus and early on in the game he surprise attacks you because he's Cyrus, you as a player are going to you're going to know to be wary of that in the future. Uh, and that's not saved in the game state anywhere. So hundreds of turns down the line, if he says his troops are just passing by, you would know better. But an AI might not. You would have to program that long-term dependence, this thing that happened hundreds of turns ago but is not explicitly stored in the game state, to play skillfully. The same thing happens in Rome Total War 2. The mood of the Senate can completely change whether it makes sense to declare war or not, even if the entire rest of the world is the exact same. It can be important to plan a decade ahead and try to shape the Senate such that you'll have the political power to make the moves you want when the time comes. How do you program in that kind of long term foresight? In the case of Rome 2 Total War, uh, this comes up all the time. How do you decide what improvements to build in what districts? How do you decide what places to attack and what places to ally with? Another reason game AI is hard is a complex game tree. In the board game Go, placing an opening stone on the 3-3 point will result in a wildly different game compared to the 3-4 point, a single step away. Michael Redmond is the only professionally competitive American Go player. He's written entire books on this difficult subject and the difference between playing on the 3-3 point versus a 3-4 point. He's written an entire book about one single opening. How do you code that? There's so much to that. Well, one way is to simulate the game and see how it goes. Imagine coding an AI to play tic-tac-toe. In this case, the number of game states is so low you could just exhaustively cover all of them, but let's ignore that for now. You could, given a board state, look at the possible moves and see how that would change the game, then pick one of the opponent's possible moves, and then repeat this process until the game ends. You could do this for each possible trajectory of moves, and having checked all of them that could possibly follow from the present board state, pick one that has a victory at the end, or better yet, pick the one that has the most victories in the end. This is fine for tic-tac-toe, where there are a tiny number of steps in that process until you get to the end of the game, but the board game of Go has a game tree that is much wider and much deeper. There are more possible games of Go than there are atoms in the universe. As it happens, however, there are some concepts and techniques from math and computer science that people have cleverly applied to coding AI in games. The game tree we mentioned, even when it's enormous, can be pruned using some clever tricks from computer science. Minimax trees and alpha beta pruning are ways to make the tree shallower and narrower, for example. In Total War Rome 2, for example, the AI uses a clever way to search the game tree called Monte Carlo tree search to decide what to build where. We won't go over the math of Monte Carlo tree search, but it's actually not that hard. It's pretty intuitive, and you can look it up on Wikipedia. In fact, we'll see later that math in modern AI isn't that hard, it's just unusual and from multiple disciplines. If you wanted to get into it, you could, even starting from just high school math. Uh, we talked about Rome 2 Total War. The biters in Factorio use some standard graph traversal algorithms from basic computer science to figure out how to get from one point to another. In fact, if you look at the Unity engine module labeled AI, you will find that it consists exclusively of these kind of path-finding graph traversal algorithms. Another way to code an AI is to cheat. If you play Civ 6, you know that at the end of the game there are graphs that you can use to see how different civilizations changed over the course of the game, how much science they produced, what their military state was, how much gold, how much religion, and so on. If you look at the chart for the gold balance of different civilizations over the course of the game, you will see suspicious spikes like this, where one player suddenly gets a ton of gold and spends all of it. What's happening there is when the AI gets declared war on it by somebody else, the AI is gifted by the game engine a huge chunk of gold, which it immediately uses to buy a bunch of military units. The reason this is in the game is because it's actually pretty hard to program an AI to recognize when somebody is building up an attack against it and what type of units it should expect so that it can prepare its defenses accordingly. It's so much easier to just cheat and give it a bunch of gold as soon as you declare war on it so that it can buy a military that will put up a kind of challenge. This might leave a bad taste in your mouth. Like, why does the AI get to cheat? But look at it from the developer's perspective. Either the developer, who is not an AI researcher, they're a gamer who likes to make games, um, tries to solve this long-standing, huge, broad field of artificial intelligence that is being worked on by thousands of research in thousands of labs across the world, or they cheat. This code to do this probably took like a day of effort if you count quality assurance and regression testing and stuff like that. It makes so much sense from the developer's perspective, especially because it doesn't negatively impact your gameplay unless you're an extremely skilled player. It takes you a long time playing Civ before you start to suspect that something is up, and longer still before you figure out what the actual problem is. But cheating with your AI is pretty common, and it's pretty common because it's efficient and easy. In Street Fighter 2, this happens all the time. You can see that when Ryu attacks Chun-Li, he uses this chain of attacks. And if you look carefully, the third attack in the chain, this low kick, goes ignored by Chun-Li. Normally, this would hit her again and force her into recovery frames to allow Ryu to maintain the attack momentum, but the CPU ignores it. Part of that is because uh, the programmer just wants to make the AI a little more competitive. If you do the same move against a person, you'll see that that low kick interrupts Chun-Li, even though it doesn't when you're playing against the computer. It cheats. All right, so that's a lot of stuff at once. Let's take a quick break for a JoJo pose. Okay. So we know that games need AI, but it turns out AI needed games more. And to see why, we'll have to step back to 2012. This is a set of examples from a famous data set called ImageNet. ImageNet consists of about 1 million images, each of which are hand labeled by what is in the image. This is some of the sample images of some of the sample labels. There are 1,000 different labels that can be applied to these pictures, and the whole point of ImageNet was to drive the ImageNet Large-Scale Visual Recognition Challenge, where every year people would compete to write a program that would be presented with an image, and the program would have to tell you what the most appropriate label was. This is a surprisingly difficult thing to do. This XKCD, published in 2014, expresses why it's strange that that seems like a thing that we do all the time without even thinking about it, but it's very difficult to program. Well, when people started benchmarking their programs against ImageNet, they had error rates of like 30%, and then somebody would improve on it and make it like 29.1%, and somebody would improve on that and make it like 28.9%. Very slow incremental progress. And that was the case for the first 2 years, 2010 and 2011, of the ImageNet challenge. But in 2012, the error rate dropped precipitously to something like 16 or 17%. A bunch of researchers, instead of programming a program to recognize what is in an image, they let it learn by itself using machine learning, and specifically a technique called convolutional neural networks. It's difficult to overstress how significant this improvement was. Usain Bolt runs the 100-meter dash in like 9.8 or 9.7 or something like that, and that's considered mind-blowingly good. The fact that it's like 100th of a second faster than somebody else. Imagine somebody shows up to the Olympics and runs it in like 7.8 seconds or something like that. That's comparable to the order of magnitude difference that we saw in 2012. And since 2012, every single winner and most of the submissions in total use that same convolutional neural net technology with ongoing developments and improvements. We don't even run ImageNet anymore because, as you'll see from the graph, the winning competitors are better than humans. So, like, what is even the point anymore? A convolutional neural network works by like stacking a bunch of kind of sub-recognition engines, like end to end, with some linear algebra bits at the end. And the goal is to get it, of course, to recognize what's in the image, But rather than telling it what to scan for, the machine learning approach is to give it a bunch of information, like pictures, and the actual correct labels, and it makes a guess and determines how wrong it is, and uses some math tricks to figure out exactly how to change itself to be a little less wrong, and it just does that over and over, millions and millions of times. So you don't even have to program it. You just let it learn on its own. All you need is the data. So this single event in 2012 by itself ignited the massive explosion in the AI revolution that we know today. And so, of course, people started to think about what else can you do with it. So the this convolutional neural network approach is part of a subfield of machine learning called deep learning. Um, and people realized this is really powerful. That technique had always been around, but it had never been so successful all of a sudden like that. So people started to look for other ways to use these neural networks. Clearly, neural networks had the capacity to learn very complicated things. Let's just give it a game state, have it output an action, and give it the outcome of the game. Well, it didn't work for a couple of reasons. One is the credit assignment problem. If you're trying to guess whether or not there's a bird in a picture, you make your guess and you immediately discover that you're wrong and how wrong you are, or that you're correct and how correct you are. If you're playing a game of chess and you make a move, you don't know whether that move was good or not until the end of the game when you determine who wins and who loses. Even then, how do you know which of your moves are most responsible for you winning that game? Certainly not all of your moves were good, even if you won. Some were better than others. So how do you know which ones you should play again in the future and which ones you should not? Luckily, the field of reinforcement learning, another subfield of machine learning, had some answers ready to go for that. Um, in 1992, a researcher used reinforcement learning to learn to play backgammon at a human level. So why couldn't you do the same thing? That backgammon program used a linear estimator in the reinforcement learning approaches, and so researchers just took that same approach and lifted the linear estimator out and replaced it with a neural network, and it didn't work. The neural network simply wouldn't learn. And it took a bit of research to figure out what was going on and why it wasn't working. Research is ongoing to this day. But in 2015, a team of researchers at a company named DeepMind figured out a way to make it work, a technique they called deep Q learning. Basically, one important thing they discovered was not to make it learn from the game directly, but to remember a bunch of games that it had played previously and learn from those memories, not the specific game being played right now. Another was to get the network to predict not actions, but action values. What is the value of each possible action? Sounds similar, but the difference is crucial. So to demonstrate, the team got a deep Q network to learn to play Breakout, which we see here. The team also got the same approach to learn to play other classic Atari games like Pitfall, Pong, Sequest, Space Invaders, etc. You can find footage of those on YouTube. These games were absolutely critical. Games provide a deterministic, parallelizable, consistent environment for these AI agents to learn from. Historically, agents for AI were either physical, which meant they were slow and would break and had to be physically reset, or hand coded, which was expensive and slow and not what the researchers are typically good at. Um, what we can see here is the process of this. This is the result of a neural network using this deep Q network approach to learn to play Breakout. At first, it's just okay. It looks like it's somebody who knows how to play the game, but has only just started, or only kind of gets how the input relates to the actions of the game. This is pretty normal. We would kind of expect this conceptually, like when you're learning, you get progressively better over time. Um, Letting it train for a little bit longer, it plays very skillfully. This is kind of the goal. This is what researchers set out to do, and this is what they wanted to find: is how you could get an AI to learn to play like an expert on its own. And they didn't tell the AI anything about the game. In fact, the only thing that the AI is getting is the score and the pixels that it actually sees on the screen. What was unexpected that these researchers found in 2015 is that if you let it keep learning, it kept improving. And eventually it learned that the way to really make the money in the game is not to just bounce the ball into the bricks like a rube, but to trap it in the roof above the bricks. So you get a bunch of points very rapidly. This is sort of an ongoing thing. Now that's the goal. When people train an AI, It's good to get human level performance, but really the real magic is getting it to exceed human performance. For some reason, the Deep Q network approach struggled with other games. It couldn't play Qbert, it couldn't learn to play Montezuma's Revenge, and others. Research is ongoing about why that is. We know a little bit better than we did back then, but this was a huge breakthrough. Researchers scrambled to apply this approach to other games and other environments, and companies noticed too. Uber had been working on developing self driving cars for years, and one of the things they struggled with was an accurate enough car driving simulator, one with traffic and collision detection, and momentum and friction and pedestrian and roads and signs and lights and lane lines and weather. Um, do you know of any place that you could find a high resolution driving simulator like that? So, how do you code an AI? Don't. You let it learn on its own. In the 90s, Deep Blue famously beat Garry Kasparov, at the time the reigning world chess champion in chess. This was a huge milestone. This was the first time that a computer had beat a human chess professional under tournament conditions. And this AI was coded specifically and solely to beat Garry Kasparov. It was given a bunch of his, they researchers took a bunch of his games and hand coded if then statements for a bunch of specific things that Kasparov was like known to do, and it took them quite a long time to do it, and it eventually beat Garry Kasparov in tournament conditions, and that was like a big deal. Conversely, when AlphaGo beat Lee Sedol, the top Go professional, in 2016, I think, they didn't hand tune it to play against Lee Sedol. They gave AlphaGo a bunch of human games to learn from so that it would learn some basic concepts about the game, and then they let it play against itself over and over, millions of times. A human can probably play maybe 5 games of Go in a day if you're really hitting it hard, and even that's exhausting, so you can't really sustain that. AlphaGo can play thousands of games a day, every day, nonstop, and that's what it did. So AlphaGo, you could argue, was not actually coded, it just learned on its own. Of course, it was coded to learn on its own, but the programmers didn't code it specifically to beat Lee Sedol. So now it's games for AI, not AI for games. Researchers immediately realized that there are already tons of high quality environments that could be simulated in games. Self driving car companies trained AI to drive using Grand Theft Auto. Defense companies train fighter pilot AIs in Ace Combat 4. Logistics companies train scheduling AIs in Overcooked, things like that. This is a video from, I think, a hobbyist researcher using multiple copies of Grand Theft Auto at once to train AIs how to drive down a highway and deal with things like traffic and weather. So now games are driving AI instead of the other way around. In 2020, the AlphaDog tournament was held, where companies were encouraged to code a fighter pilot AI, and there was a tournament where those AIs competed with each other, and whoever won got to fly in 5 dogfights against some of the top instructors at the Air Force Fighter Weapons and Tactics School, or whatever it's called. This is the end of that tournament. This is the spoilers winning group called Heron that gets to dogfight against a fighter pilot call sign Banger uh, in a simulated dogfight, and they execute 5 dogfights against each other. And spoilers again, the AI wins all 5 fights. Not only does it win, it never suffered a single hit. And not only did it never suffer a single hit, it was never even in a position of disadvantage against the human pilot. And these are some of the best fighter pilots in the world. Now it's not the end of the world for fighter pilots. There were some like restrictions and limitations on this. There were no missiles. The pilots were only allowed to use guns, and I think they were pretty liberal with the amount of information about the environment that they gave to the AI. So there's still room for like research and improvement, and this is not the end of human fighter pilots, although that may be coming. Um, but you should go and check this out on YouTube. The whole tournament runs with fighter pilots and engineers and computer scientists giving you commentary about like what's happening tactically and what's happening technically, what the AI is thinking and doing behind the scenes, things like that. So, how did we go from the very primitive AI in like Pong that you see on the left to the almost beautiful Monte Carlo tree search and reinforcement learning algorithm style of AI that you see in the upper right that AlphaGo uses, and to the complex system of systems of multiple layers of AI from the computer vision models that are doing these boxes and recognition of the real time video, as well as the AI that's taking in that video and several other videos from other cameras. And deciding how to drive the car, like how to turn the steering wheel, how to press what pedals, and things like that. Well, it should go without saying that it's gone beyond the if then world. Anyone can design, if not code, an AI. If you were to design a thermostat, you might design some logic that says if the temperature goes below the setting, increase the gas to the heater. And you could legitimately call that AI. It's a single interpretable handwritten rule that has two inputs, the temperature and the setting. It is also built upon an understanding of the environment it's in. Increasing gas to the heater is known to increase temperature. When there are a lot of options or there are future decisions to be made, more complicated techniques are required. A good example is the tree search. We talked about Monte Carlo tree search, um, and even that needs some editing to make it useful. The tree search has a lot of states to visit. Connect 4 is a very simple game and has 4.5 trillion possible game states. Checkers is a pretty simple game, and it took researchers constant number crunching over 18 years to check every possible game position. Tree search becomes more feasible if you prioritize. Rather than checking each possible move in each position, only look at the most promising moves at each decision point and follow up on those. This is easier said than done and wasn't practically possible in non trivial games until about 5 years ago. One of these points of research has been by applying the subfield of machine learning that we talked about called reinforcement learning. Assessing the value of each possible move at the point in the tree search sounds great, but if you knew which moves had the highest value, you wouldn't need to do the tree search, you could just play the best move. Through reinforcement learning algorithms, it's possible to derive what's called a value function, the equation for which you see here in the lower left, to calculate the relative value of a given state or action. These derived functions are only approximations, so there's little bits of error here and there. So the tree search is still valuable. And in fact, this is how AlphaGo beat the top Go player in 2016. The equation in the lower left looks big and scary, but I assure you it looks scarier than it is. If you've taken one semester of algebra and one semester of calculus, you know all of the math that you need to understand what that equation is doing. It's written this way because that's kind of an industry standard, and it comes from a book by two researchers named Sutton and Bartow, who published kind of the seminal work on the topic, which is available for free online. It's literally just called reinforcement learning. So go and check it out. They walk it through you step by step, and you really can learn this stuff. It really is possible. So there's a lot of potential with AI, but there's a lot of problems too. This is the result of an AI trained to track the soccer ball. It mistakes the bald head of the ref as the ball and completely ignores the actual game. That's a problem. Then there's this passport photo. Can you read the circled text? It says the photo you want to upload does not meet our criteria because subject eyes are closed. His eyes aren't closed, man. He's just Asian. The AI is racist. Of course, the AI isn't consciously racist. Nowadays, people have done a lot more research, and research is ongoing about the ethics of machine learning and artificial intelligence. One of the things that we've discovered is if you let an algorithm learn from biased data, it will learn a biased opinion. So, in facial recognition, like in this case here, it's very common for large data sets of faces, perhaps labeled eyes opened or eyes closed, to consist mostly of white men. There are a couple of reasons why that might be, but the science side of it is that a model trained to recognize open or closed eyes from a data set that consists mostly of white males is going to get really good at understanding the parts of a white male face, but will struggle to generalize to other races and genders. This is the image from research done to try to get a hexapod robot to learn to walk on its own. The robot was told to maximize forward progress and minimize foot contact with the ground, and it learned to do that by flipping onto its back and using its knees to walk. One of the challenges with machine learning is the other side of the coin of its biggest strength. It learns on its own. Sometimes it finds amazing solutions that we didn't expect, like in Breakout. Sometimes it finds solutions that we don't like the hexapod robot. All right, let's take another JoJo break. All right. So what does this mean to you as a gamer? Well, it means better AI and smarter AI. You can see in this video that it's a game of hide and seek that the researchers are trying to train the seekers in orange to beat the hiders in blue and vice versa. You can see over however many iterations they do that the hiders eventually learn to block off the entrances to their little pen so that the seekers can't get in. Eventually, the seekers learn to recognize this, and you'll notice there's another block available in the little pen where they're operating, that ramp in the upper left, and they learn to use that to defeat um, the blocking and locking strategy that the hiders come up with. Eventually, the hiders learn this also, and they learn to steal the ramp first before they lock the blocks in place to keep the seekers out of their little pen. Something similar was done in this environment, but you'll see that the seekers learn a little trick. There's a bug in the physics engine that lets them surf on a block that would, if you were to reasonably imagine how this environment works, you wouldn't think would be possible. And in the real world, it's not. This is only possible, like I said, because of a math error in the physics engine underlying this. Uh, Again, we don't get to influence, but only so much, what the AI learns and how it learns to operate. Sometimes it will learn to cheat like this because to the AI, it's not cheating. It's just learning what to do in its own environment. Uh, but also keep in mind um, that even though this happens all the time, it happened with AlphaGo in Game 1. AI played move 37, a move so brilliant and creative and out of the box that everyone watching, including all the professional commentators across 4 countries, were surprised and shocked by the move. No human would ever play this move, was the common refrain. And it only took a few more moves before everybody recognized what a brilliant move 37 was. But remember that this kind of AI is crazy expensive. I couldn't find the article where I read this, but a game developer working to digitize a board game tried to apply the AlphaGo technique to their game, and they found that it was just too expensive. It was working, definitely. They could watch the AI improving in the numbers in the graph that reported summary statistics, but they would have had to pay hundreds of thousands of dollars for the compute power to get it to learn to get to an acceptable level. And that's just for like some mid-range studio. AlphaGo was funded by Google. And AlphaGo trained for weeks on hundreds of machines, specialized machines, to learn what it did. Even big AAA studios like Blizzard or Microsoft or whatever would struggle to justify spending that kind of money just to make an AI that like doesn't cheat or is better or more creative or whatever. Lots of AI tools do exist, and they're being developed more and more to help people who make games. We'll talk about you devs in the next section. Make them, and that's great. But research only progresses so fast. It might mean faster game development, as some of the game development steps are assumed or aided by artificial intelligence, but probably not cheaper games. Typically, in the history of games, AAA games have stayed pretty much the same price. It's just they get turned around much faster or at the same speed for a much larger scope. Um, and there's also probably a lower barrier of entry for indie devs. So we'll talk about how devs can use AI in the future, but you can lower the risk or cost of making a game, which is important for indie devs who will make like a unique game with a bizarre mechanic or whatever, which would normally be a high risk because you're spending all this time in a game that people might not get. And if there's less effort because the AI is doing some of the work for you, it's easier to take that risk. So what does it mean to you as a dev? It means higher AI expectations. People are not going to be satisfied with the stupid AI anymore. Cheating will probably still work, and cheating AIs will always be around. Um, but the expectations are only going to increase as these things keep making headlines and artificial intelligence enters the non-technical lexicon more and more often. Um, Creative tools are getting better rapidly. A lot of game developers, particularly indie devs, are just devs. They're not musicians, they're not writers, they're not artists. And so often the hardest part, the most expensive part, the most time consuming part of game design is the media assets, the music, the sound effects, the um, script and dialogue, the voice acting for the script and the dialogue, the backgrounds, the portraits, all kinds of stuff like that. Um, there are tools out there, and we'll cover some of them, that you can use to do these things for you. They're not perfect, but a lot of them are free and easy. And if all you want is done and you don't need perfect, it's fantastic. And as an artist, we'll see how you can use those in the future too. There are also coding tools. People have been trying to get artificial intelligence to write code for 5, maybe 10 years now. Um, and we're just starting to make progress. GitHub Copilot is an example of that, but it's still pretty weak. Progress is progress, and it's impressive for what it's trying to do, but we're a long way from typing what you want the code to do and have an AI generate code that does that. So what about these tools, these creative tools? Where there are a lot of visual tools too. There's neural style transfer, which is a technique that NVIDIA pushes really hard that will take the content of one image and the style from another image and fuse the two. Um, there is, right after I gave this talk at MagFest, NVIDIA published GauGAN, which is a paper describing a tool that they use, the use of which you can see more specifically on the right here, where you use simple colors, each of which is aligned with something, like the gray is water, and the teal is sky, and the dark gray is cloud, and the brown is rocks. And you color in just like kind of a segmentation map, they call it, to tell the AI what sort of substance you want in what place. And it generates that for you. You can see as he's drawing clouds, it actually makes clouds. And you can see that the rocks align with the rocks that the user has put into the picture. And you can even see that the AI knows that like water around the rocks tends to be shallower, or that water flows around rocks, and stuff like that. GauGAN, GAUGAN, is available for use for free. You can go and use it, and it's very easy to use. Upscaling and interpolating video is an emerging technology that's getting better and better. If you want to make like stop motion video or a 2D animation or something like that, you can use tools like DAIN or Anime Interp to take your 15 frames per second video and interpolate it to a 60 frames per second video. So you only have to do 1/4 of the work. There are tools for generating or altering or inpainting things. NVIDIA Canvas is another such tool. You can see a tool on the lower right where you take one picture and pick a different style, and it applies that style to it, either weather or time of day. There's tools listed here. FantasyFaces.com, for example, uses a generative adversarial network to generate hand-drawn fantasy faces of the kind that we used to draw on our character sheets, playing RPGs and stuff like that. If you are concerned about this as an artist, if you're thinking, man, how am I going to make money if who's going to buy my work when you could just do this stuff for free? Well, go and use the tools. Again, they're not perfect. And in the same way that the Moog synthesizer didn't get rid of musicians forever, musicians just started to use these synthetic tools in the operation of their craft, so artists will start to use artificial intelligence augmentation techniques to do their art. So if you imagine somebody asks you to draw a picture of a mountain range in each of the 4 seasons, instead of drawing 4 different drawings of that mountain range in 4 seasons, you draw one and use an AI tool like this to restyle it to match the other 3 seasons. You just got 4 times more efficient for free, and the customer still gets the same quality product. The things that the AI does, again, it's not perfect. A lot of times you'll see problems and imperfections, and you as an artist can use this generated art as a base and then restyle it to match your style, or edit it so that it doesn't look quite as wonky, or add some like little specific things. Um, the Gauguin tool, early version of which you see in the upper right, is good at generating landscapes, and it can generate some buildings too, but it's not great at generating like medieval castles. So if you want a medieval castle on a cliffside, you could use Gauguin to generate a very realistic looking cliffside, and then you, as the artist, draw the castle on top of that. So it hasn't replaced you, it's become a tool that you use in your toolbox. There are audio tools too. Um, for um, voice generation, text to voice, the tools are getting better and better. You can see the name of some tools that I just Googled around and found here. So if you write your own voice lines or whatever, and you don't have the money to pay a voice actor, you can use AI to generate those voice lines for you. Again, they're not perfect, and often you can tell that they're computer generated, but they're way better than they used to be, and they're getting better all the time. You can find similar tools for music and sound effects and background music generation as well. Text is another big area where generative tools are becoming more and more available, and there's more every day. GPT-2 is a giant, now obsolete natural language processing model that could generate text that was so realistic, it was easily fooling people into thinking that it was written by humans in a lot of cases, not every time. There was a lot of hype about it being a potential tool for disinformation of such power that the developers didn't release it because they were afraid of the potential ramifications for like just putting garbage misinformation on the web or whatever. Who knows how much of that was PR and hype building or whatever, but it is very good. If you want to try it, you can go play AI Dungeon, which is kind of like a little AI powered dungeon crawler game where you just type what you do, and the AI uses that as a prompt to generate what, I don't know, like a DM would tell you, or what the like text-based game would tell you happens or whatever. Give it a try. It's free. It's pretty interesting and pretty impressive too. So here's the bottom line. Here's where we are today. Games need artificial intelligence and they provide an environment. Research needs an environment and it provides solutions. Devs need solutions and they make games. Gamers pay for games, which leads to economic incentives to make more games. So it used to be that AI was a tool that games relied on to make themselves playable. Then it became a two-way street where research was using games as environments for learning, and now the loop has closed itself, where it is one self-contained, self-feeding Ouroboros of a system. So you, as gamers, playing and making and selling games, are actually contributing to the AI revolution and helping move human knowledge and research and technological understanding to the next level. So keep doing what you're doing. If you're interested in some of the people I mentioned, here's who I talked about. Freemason Live is a Twitch streamer who plays first-person shooters like Tarkov and Sea of Thieves. Jorbs is a strategy game streamer on Twitch. He plays primarily Slay the Spire. Potato McWhiskey is a YouTuber who does Civilization games. And Michael Redmond is that American Go professional I talked about. He actually recently started a YouTube channel. It's pretty good. Check it out. And then if you're interested in more of my content, you can find my handle in the upper right there. I'm really only on YouTube and Twitter these days, but just give me a shout. I'm around. Thanks for watching the video, and hit me up with any questions you have. Thanks.